Good day, everyone. We'll be considering the classification of signals in this lecture. And to begin, I think it is worthy of note to understand that the continuous time signals and the discrete time signals can be further categorized into a number of signals, which we'll be considering right now. First of which is the analog signal. Analog signal. And this is a continuous time signal, say S of t, that can take on any value in a continuous time interval, say from negative infinity to positive infinity. A simple example of such a signal is something like this. This is the time scale. This is the amplitude scale. Then we see the signal value ranging from positive to negative infinity. And then we have digital signal. And this is a discrete time signal. Note that the analog signal is a continuous time signal, and the digital signal is a discrete time signal. Say x of n that can take on any finite number of discrete values and have something like this. Say it's a 1, a 0, and on and on. So say this is a 1, this is a 0, this is a 1, this is a 0, this is a 1, this is a 1. So here you see that the amplitude parameter takes on a finite number of values. Okay, so that 1 or 0. Then we also have real signal. Now, a real signal is a signal whose value is a real number. So the value here is a real number. While a complex signal is a signal whose value is a complex number. So let's take a complex signal, say S of t is a complex signal, such that we have the imaginary component, say x of n t, plus the real component rather, s of n of t, plus the imaginary component, say x of m of t, where x of n and x of m are real values, okay? Or better still, the real signals. And here j, which makes for the imaginary component of this complex signal, is given a square root of negative 1. Okay. Another classification we have here is the deterministic signal. So this is a signal whose values are completely specified. So the values are completely specified. For any given time interval. So an example is a step signal. So we have a step signal. T, S of t. Then we have the value A. Okay. So in other words, S of t is the same as A. So since the value can be determined or is explicitly specified, say it is a deterministic signal. Then we also have a random signal. Meaning the value is not explicitly specified. So this is a signal whose value or values are random at any given instant of time. Okay, and an example of this is a noisy signal, say a speech signal. Okay, abruptly varying amplitude value. Okay, so it's T, and here is S of T. That's the origin. So since the amplitude values cannot be easily determined, they are estimated using some statistical techniques. Then we also have even signals. Now, even signals or signals. So these are signals that are signals that are symmetrical. Above the y axis, or better still, the s of t, x of t axis. Okay, so here, what this implies is that the time reverse version of the signal is the same as the original signal. That's for the discrete component. Let's go to okay. So mathematically, when the signal remains the same on performing time reversal operation, then it is an even signal. So how do we perform time reversal? Okay, so let's take an example. So we should note now, okay, let's change to follow. We should note now that time reversal is that operation on signals that multiplies the time scale of the signal by some parameter, say alpha, for which alpha is the same as -1. Okay. So this operation is meant to perform folding operation on the signal. Okay. So let's assume we have a signal, say, at the input to a system. So let's assume this is a system, okay? Now we said we want to perform time reversal. So for alpha is the same as -1. So this is the input to the system. And then this is the output, okay? Output system. So if we have a rectangular signal waveform, say of this magnitude, 4, and then this is S of t, this is the time scale, t, the origin. Then, if we perform time reversal on this signal, it means that this time t equal to 0, so let's change this color. This time t equal to 0 multiplied by -1 is still 0. So we still have 0 here. And then this with an amplitude of 4, okay? And then positive 4 times -1 will give us -4 on the time scale. So we're going to be having -4 here. And then the time reverse version of the signal looks something like this. Okay. So meaning we are folding the signal about the x of t axis. Okay. So that's time reversal. So how then? And now for a signal to be even, it implies that given the original signal s of t, once the time reversal operation is performed on it, say s of minus t, then this signal will be even if s of t is the same as the time reversed version of the signal. So let us consider an example of a time reversed signal. So let's say we have a system. Okay, it's a system that performs the folding operation. Then we have a rectangular waveform of t. So this is -2, +2, with an amplitude of 2. So if we perform time reversal on this signal, then at the output, this is the input, and this is the output, the system. Then we should get something like this. S of t is the time scale. So this parameter operates on the time axis. So negative 1 times 1, then 0 times -1, then +2 times -1. So this is going to give us, times 2 rather, this is going to give us -2 times -1, give us 2, 0 times -1, that's 0, +2 times -1, -2. So in other words, we're going to be having a replica of the same signal. This is -2, this is 2, then this is 2. So since the signal, given the signal s of t and the time reverse component, since they are the same, then this signal is an even signal. Now let us look at another signal, which is odd signal. So this is a signal that is antisymmetrical above the x of t axis, or better still, the y axis. And this implies that the time reverse component of the signal is the same as negative S of t. That is, for a discrete signal component, we have negative S of t. So it is to be noted that an odd signal, an odd signal must be zero at time t equal to zero. So meaning all odd signals will always pass through the origin. So an example of an odd signal says something like this. See, passes through the origin. Okay? So that is the time axis, and this is S of t. So let's take an example. So given a system that performs the folding operation, this is the input, and this is the output. If we have a signal, say triangular signal, 0, 2, this is t, so S of t, then in performing the folding operation, see that this is what we get. It's 2, so t, t. So let us consider some more examples. So another example. So now we want to show that the product of two even signals is an even signal. So let S of t be the same as S of 1 of t times S of 2 of t. So if S1 of t and S2 of t are even, then the time reversed version of the signal will give us S1 of minus t dot S2 minus t. Then we already know that for an even signal, S of minus t is the same as S of t. So this is going to give us S1 of t dot S2 of t, which gives us our original signal, S of t. Hence, S of t is even. Okay. Now, let us justify the claim that the product of two odd signals is an even signal. So just like in the previous case, let S of t be the same as S1 of t, the product of S1 of t and S2 of t. So if X1 of t and S2 of t are both odd, Then S of minus t will give us S1 of minus t dot S2 of minus t. Now recall that for an odd signal, S of minus t is the same as minus S of t, right? So this is going to give us minus S1 of t, product of minus x1 of t and minus S2 of t. So minus times minus is going to give us plus, so this is going to give us S1 of t dot S2 of t, which is the same as the original signal, so which is equal to S of t. So hence, S of t, see. Okay. So let's look at another example. That the product of an even signal and an odd signal is an odd signal. So let's S of t be the same as the product of x1 of t and s2 of t. So if x1 of t is even and s2 of t is odd, then as in the previous case, s of minus t will give us s1 of minus t dot s2 of minus t, and being that s1 of t is even, then we have x1 of t, and performing the folding operation here, we have minus s2 of t. So here we have minus x1 of t dot s2 of t, which gives us minus x of t, such that s of t is odd. So I think it is worthy of note to establish at this point that in practice, signals are usually expressed as a combination of the even and odd components, okay? Such that S of t can be represented as S of even t plus S of odd of t, okay? So we'll come back to this much later. Study. So now that we have discussed even and odd signals, let us look at another signal, the conjugate symmetric signal. Okay. Now this is a signal whose whose original signal, say S of t, is the same as the complex conjugate of the time reversed version of the original signal. So in other words, we have the original signal, S of t, get the time reverse version of the signal, and then take the complex conjugate of the time reverse version of the signal. Okay, so this is minus. See, okay? So this signal S of t will be a conjugate symmetric signal if and only if S of t is the same as S of star of minus t. Okay? So this is the conjugate. This is the condition for us to have a conjugate symmetric signal. Okay, but at this point, we need to establish the fact that given a signal S of t, say x1 of t plus js2 of t, the complex conjugate of the signal S star of t is the same as s1 of t minus js2 of t, such that the complex, this is the complex conjugate, not the conjugate symmetric. Okay, we need to get that, because at this point the sign of the imaginary component changes. Okay, but by definition, to obtain the conjugate symmetric signal, first we have to perform the folding operation on the signal, such that, say, S of t is given as S1 of t plus js2 of t. Then in performing the folding operation minus t will give us S1 minus t plus js2 of minus t. Then the complex conjugate of the time reversed version of the original signal will now be given as S1 of t minus, oh sorry, this is minus, let's clean this up. So S1 of minus t minus j S2 of minus t. So when this condition is satisfied, that is, S of t being the same as the complex conjugate of the time reverse version, then we say this signal is conjugate symmetric signal. So we also have conjugate antisymmetric signal. So by definition, S of t is the same as minus the complex conjugate of the time reverse version, such that if S of t is given as S1 of t plus js2 of t, then the time reverse version will be given as S1 minus t plus j S2, sorry, S2 of minus t. And here we've performed time reversal. And afterwards, we take the conjugate of the time reverse signal, which is S1 of minus t minus, this is plus, okay, minus JS2 of minus t. So this is the complex conjugate of the time reversed version. And then we now perform amplitude reversal. That is minus ST S1 ST, and this becomes plus by performing the amplitude reversal J S2 ST. So this is amplitude reversal. Okay. So when this condition is satisfied, then we say the signal is conjugate anti-symmetry. So the point now is, how do we perform amplitude reversal? Okay. How do we perform amplitude reversal? Okay, let's check an example. Now we've talked about time reversal. So just like time reversal, here we are going to be multiplying the amplitude or the signal itself by a parameter. So we say that amplitude reversal is a special case of amplitude scaling. Okay, so amplitude reversal. So let's assume we have a system, say where k is the same as probably a particular parameter which is unknown. Okay, so if we have a signal at the input, say s of t, then at the output we expect to get some value y of t being the same as k times s of t. Okay, so once this operation is performed, we see that this parameter k performs some level of amplitude reversal. Okay. So, if for instance, we are given a signal into this system, let's change this color. So let's say we have a system k equal to -1, okay? And then we have a signal into the input, so we expect the amplitude reverse version at the output. So if we say we have the signal, say this is 3, and this is positive 3t s of t. So at the output, this is t, this is s of t. Should we multiply this amplitude value by a -1? So that's -1 times 3. So we're going to have -3. So we're going to have it somewhere here. It's 3. Okay. So I'm going to be plotting that. Okay, so this is a simple way to perform amplitude reversal of a signal. So let us talk about another type of signal, which is periodic signal. So we say a continuous time signal, S of t, is said to be periodic when we have a positive non-zero value at the time period. So assume we have a signal with a period t, then S of t is given as S of t plus t for all t, okay? Meaning the signal is said to be periodic with period t if there is a positive non-zero value of t given this condition. And now the fundamental time period t naught is the smallest positive value of t, so value of t for which the signal is periodic, such that the fundamental frequency is the same as the inverse of the fundamental time. Now, in a similar vein, the discrete time signal, or better still, sequence, S of n, is said to be periodic with period n if there is a positive integer n for which S of n is the same as S of n plus n for all values of n, such that the fundamental time period n naught of the sequence S of n is the smallest positive integer n for which the sequence is periodic, such that the fundamental frequency f is the same as 1 over n, or n naught, okay? F naught equal 1. So when the signal or the sequence is not periodic, we say it is non-periodic, okay? Or aperiodic. We'll come back, to resolve some of these signals in more detail. And to quickly run through, let's talk about energy signals. So we say that a signal S of t said to be an energy signal if and only if the total energy is finite. That is, 0 less than E less than infinity, such that the average power P is the same as 0. Okay? So here, we should note that energy, or the energy signal, must be absolutely integrable. Okay? That is, taking the integral from negative infinity to positive infinity, the mod of the signal S of t dt must give us a finite value. So it must be less than infinity. And you'll realize that this is also a condition for a signal to have a Fourier transform. Okay? So energy signals will always have Fourier transform. Okay? And the next component to consider here is that the energy is the same as the area under the graph, which is mod of S of t squared. And then the average power must be 0, such that P takes the limit for t tending to infinity E over t. So as t tends to infinity, no matter the value of E, this reduces to 0. Okay. How about power signals? Now, a power signal, S of t, or a signal rather, S of t, is said to be a power signal if and only if and only if, and only if its average power is finite, such that the average power takes on the value between 0 and infinity, but less than infinity. And then the energy, total energy, must be infinite. So, one point to note is that periodic signals are power signals, but power signals may not necessarily be periodic signals, okay? And the final group we'll be talking about here is the neither energy nor power signal. Neither energy nor power signals. So for any given signal that does not obey the principle for the energy and power signals, we say they are neither energy nor power signals. So in other words, the energy value must not necessarily be within this range, and the power value must not necessarily be within this range. So we now say such signals are neither energy or power signals. Okay, let's look at a few examples before we call it a day in this lecture series, or in this lecture. Okay, so let us verify. So let us verify if the following signals are either energy, power, or neither energy nor power signals. Okay. So we have the first of the signals, S of t is the same as epsilon A. So t, U of t for A greater than 0. Now, do note that the unit step function knocks off the imaginary component of the signal, or the negative, not imaginary, negative component of the signal, such that only the positive part of the signal uh, appears at the output. So, for us to verify if this is either an energy power or neither energy nor power signal, let us estimate the energy for the signal, total energy. So we have negative infinity, positive infinity, S of t squared mod of S of t squared dt. And this gives us negative infinity to positive infinity, epsilon minus 80 u of t mod of this dt. Now recall that u of t ranges from 0 to infinity. Hence, the step function changes the limits of integration such that we now have 0 to infinity epsilon minus 80 dt. And now this gives us epsilon minus 280 over minus 2a from 0 to infinity. So we have 0 minus minus 1 over 2a, which is equal to 1 over 2a. So since the energy value is finite, then we say S of t is an energy signal. Let's check out another example. S of t is the same as a cos omega naught t plus phi. Now, we already know that this is a sinusoidal signal, such that it is periodic. It's periodic with a period t naught equal to 2 pi omega naught. Okay. And now we'll have to estimate the average power of the signal. That is P 1 over T naught, 0 T naught, S of T squared dt. So once we substitute the fundamental time period parameter here, we have omega naught over 2 pi, 0, 2 pi over omega naught, then a squared, because this mod S of t squared, cos square omega naught t plus theta. dt. So using our trigonometric identity and integrating, we have a squared omega naught 2 pi, taking our limits of integration, 1 over 2, 1 plus cos 2 omega naught t plus 2 theta dt. Then by integration and substituting the limits of integration, we have a squared over 2, which is less than infinity. And this justifies our original claim that periodic signals are power signals. Let's look at another example. Say S of t is the same as the ramp function tu of t. Okay, so if we take the limit for the energy for t tend to infinity, so negative t over 2, t over 2, s of t squared dt, then that's going to give us integral, because the unit step function gives us a limit of integration from 0 to infinity, okay? Positive infinity, so that'll be t squared dt. And this gives us, for t tend to infinity, t over 2 cubed over 3. And as t tends to infinity, then we have this value tending to infinity. Okay. So now, with this, we are not sure because we want to know if it's either a power signal, because it's certain it's not an energy signal. So we want to confirm if it's a power signal or a neither energy nor power signal. So we have to estimate the average power. So we take the limit again. T tends to infinity. T still 2 t squared dt. And then if we take the limits for which tends to infinity or 0, remember the unit step function gives us the limits of integration from 0 to t 2 t squared dt, and then just like in the energy estimation, have 1 over t over 3, t over 2 cubed over 3. Once again, this tends to infinity. So hence, S of t is neither energy nor power signal. Let us look at a discrete signal. So let's say the sequence S of n is given as minus 0.5 to the power of n u of n. So once again, since it's a discrete signal, we replace the integral or integration component with the summation, because we're dealing with discrete values. For continuous time signals, since they're continuous signals, we integrate over the limit. So for n, taking a value from negative infinity to infinity, then s of n squared. Okay. But here it is interesting to recall that the summation of n, taking a value from 0 to infinity, k to the power of n by way of expansion, and for n tends to infinity, summation n for the 0 for kn to n minus 1, we have that n to infinity 1 minus k over n over 1 minus k, which approximates to 1 over 1 minus k. So therefore, the total energy in this case is given as n squared, which is infinity to infinity 0 to 0, 5 n n, which now gives us summation taking it from n 0 to infinity and 0.5 mod. Since it's the mod of this, then that takes care of that negative value. So we have summation n for the 0 to infinity 0. That's squared one. Squared, sorry. 5 to n, right? Which is the same as n equals 0 to infinity 0.25 n, which is 1 over 1 minus 0.25, which is the same as 4 over 3, which is less than infinity. So hence, S of n is an energy signal. Okay. So let's say finally, for today, we want to validate the assertion for a given periodic signal, say S of t, with the fundamental time period t0, that the normalized average power of S of t, that is P, taking the limit of t tangent to infinity, 1 over t, for negative t over 2, t over 2, for S of t squared dt, is the same, that is the same, as the average power of S of t over any interval t0, given by P equal to 1 over t0, taking the integral 0 to t0, S of t squared dt. Okay, so here I'll just put up a side note. That once the limit is taken such that t is an integral multiple of the fundamental period, such that t is the same as k equal to t0, then the normalized energy content of S of t over the interval t will be k times the normalized energy content over one fundamental time period. So what we're trying to say here is that P is the same as the limit for K tend to infinity 1 over K T naught times K integral 0 to T naught S of T squared dt is the same as 1 over T naught integral 0 to T naught S of T squared dt. So I'll say this is where we'll wrap up for today. Thanks for participating in this class and hope to see you some other time. So